section 8.3, multiply, divide, and simplifying radicals. So now we're going to get away from rational exponents and get back into rational exponents. You can go back and forth between the two. So to multiply, like you saw in the previous section, we were not able to multiply when we had different indexes. But if we do have the same index, then we're allowed to multiply them. So if we had nth root of a and the nth root of b, and we wanted to multiply those two, we would keep the nth root and we'd multiply what's underneath, a times b. If again we had the nth root of a and the nth root of b and the real numbers and we wanted to divide them, as long as they have the same index, we can put them underneath the same radical. But again, b cannot be 0 because then we would be dividing by 0. So whenever you're trying to multiply or divide, the first thing you want to look for is, do you have the same index? If you do not, then you have to go back to 8.2 and use rules of exponents. But in this section, we will all have the same index. So right now, if you look at the index here, there is no number, but the index is a 2. And it does say find the product and simplify. So we're going to multiply and keep them both underneath the square root, and 3 square root of 36 is just 6. Again, on the second one, the index is a 2. Remember, when it's not there, it's understood to be a 2. That means the square root. Because we have the same index, we'll put them underneath the same radical, and 8 times 2 is 16, and y cubed times y, when we multiply, we add powers, so we get y to the 4th. The square root of 16 is 4, and then we take power divided by index, and 4 divided by 2 is 2, so we end up with 4y squared. Now number 3, we look to make sure that the index is the same, and the index is a cubed root. So we'll go ahead and put them underneath the same cubed root index. And 3 times 2 is 6. And m times m is m squared, because when you multiply, you add powers. So we get the cubed root of 6m squared. There's not a number that you can multiply 3 times and get 6. And m squared, there's only 2 m's. You need at least 3 to take them out. So we are done. So what's going to happen is there's going to be lots of problems from here on out that not everything cancels out of the radical. So the next set of problems says simplify, assuming that the variables again represent positive values. When we look at this, we see that their index is a 2, and I keep highlighting it so make sure you do the same thing. And when they are separated, we can put them together, or we could try and simplify as is. I would go ahead and put them together, because when they're separated, think about putting them together to see if it makes your life easier. Now, how would that make my life easier? Because 18 and 81, they both have a 9 in common, and so 18 divided by 9 is 2, and 81 divided by 9 is 9. But then we have to re-separate them, the square root of 2 over the square root of 9. And what's the square root of 9? The square root of 9 is 3, so we end up with the square root of 2 over 3. Now some students from the very beginning would said, well, I know what the square root of 81 is. The square root of 81 is 9, and that is true. But on the 18 is 9 times 2, so the square root of 9 is 3, so we get 3 square root of 2. And then the 3 and the 9 can cancel, and we're back to the square root of 2 over 3. I think that might be a little bit more challenging way to go, so I suggest putting them together, reducing, and then separating them back up, and then taking the square roots if possible. So for example, on number 2, if we had the square root of 15 over the square root of 5, there's nothing we really can do. However, if we put them together, we can go farther, because the square root of 15 over 5, when you reduce that, gives you the square root of 3. Again, you can't just divide the 5 and the 15 as is. You got to put them underneath the same radical because they have the same index, and again, the index is a 2. On number 3, we had the cubed root of 5a over the cubed root of 8r to the 6. So if we put them together, we get the cubed root of 5a over 8r to the 6. Well, that really didn't help because we can't reduce the 5 and the 8. This is an a, this is an r, so that's not going to help. So going back to the original, can we take anything out of the top? No. So it's going to stay as the cubed root of 5a. But we do know what the cubed root of 8 is. The cubed root of 8 is 2. And we take power divided by index. So 6 divided by 3 is 2. So r squared is going to come out. So again, sometimes you're going to go down a road and it leads you straight to the right answer. Sometimes when you start it off, if nothing happens, go back and try a different way. Don't always assume it's going to be the same steps every single time. Try different things and see if it works. If it doesn't, try something else. Alright, so now we're going to get into radicals that don't completely take everything out. For example, just like this one, we were left with the square root of 3. Here we were left with the square root of 2. MyMathLab shows a little bit different than the way I'm going to show it. They want you to find the biggest perfect square that can go into 245. With the way that MyMathLab shows. I like to show where you do pairs or triplets depending on what the index is. So looking at number 1, we have 3 times the square root of 245. Again, the index is not a 3. The index is a 2. That 3 is on the outside. So I'm looking for pairs. And if we look at 245, don't just sit there and try to figure out what 245 can be divided by. Take your calculator and take 245, and you know it can be divided by 5 because it goes in evenly. So it ends in a 5, so we know this would be 5 and 49. 5's prime, so underline it. It's done. But 49's not. 49 is 7 times 7. And then underline those. So the prime factorization of 245 is 5 times 7 times 7. So then you circle pairs because your index is a 2. So the 3 is already outside, a 7 comes out, and whatever doesn't have a pair stays underneath. Now why is it just 1 7? Because it was really 49 and the square root of 49 is 7. So I just say take the pair and the pair comes out because you're taking the square root of it. So we get 3 times 7, which is 21, and we end up with 21 square root of 5. On number 2, the index is again a 2, and on this one the index will be a 3. So on the with the square root, we have no numbers underneath, just variables, so we take power divided by index. So 4 divided by 2 is p squared, none are left underneath. 8 divided by 2 is 4, so q the fourth comes out. And 6 divided by 2 is 3, so r cubed comes out. Nothing is left underneath the radical because we were evenly dividing everything by 2 and with the remainder of 0. So now we have the cubed root of 54. Again, don't just stare and think about what could those factors be. You know it's even because it ends in a 4, so it could be divided by 2. So take your calculator and do 54 divided by 2, and that would be 27. 2's prime, 27's not. Now if you're okay knowing cubed roots, you already know you have a cubed root, but we'll continue on. That's 3 times 9, and 9 is 3 times 3. But don't circle pairs. This is a cubed root. If it's a cubed root, you have to circle triplets. If it's a fourth root, you have to circle things that are in 4s. So don't circle pairs here. You need to circle all 3 3s because you need 3 of them to come out. Because again, it's a 27, and there's a cubed root of 27. So a 3 comes out, and cubed root of 2 is left. I have lots of students forget the index. So please, anytime it is bigger than a 2, make sure you are highlighting it and putting the index back in. You can't switch a cubed root to a square root. All right, let's continue trying some more of these. Again, we have a cubed root of 48, h to the 14th. So 48, I think of 48 is 6 times 8, and neither of those are prime. 6 is 2 times 3, so I'm going to underline those values. 8 is 2 times 4, so I'll underline, and 4 is 2 times 2, so I will underline. Now again, the prime factorization are just the numbers that are underlined, so you don't have to worry about the 4, the 6, or the 8 anymore. So we're going to circle triplets. We do them out, but what's going to be left is that 2 times 3, so 6 is going to be left under the radical. So 2 comes out. I'm going to leave a little bit of space because we still have to work for the h, and 2 times 3 is 6. So I get 2, and then we're going to work for the h's, and cubed root of 6. Now, look at the 14. We take 14 and we divide by 3. Most of the time we've had it going evenly, but not this time. 3 can go into 14 4 times with the remainder of 2. So this tells me how many come out. this tells me how many are left underneath. So the whole number comes out, so we have h to the 4th on the outside, and then we have the power of h squared left on the inside. So again, this number is the power that comes out, and this one is the power that stays underneath. Alright, so looking at number 5, we have 4 times the cubed root of 250 y to the 5th. So again, let's go ahead and do some factorization. 250 would be 10 times 25. 10 is 2 times 5, and those are prime, and 25 is 5 times 5. It doesn't matter how you started off, you'll all come out with the same prime factorization. So we're going to circle triplets because the index is a 3. So right now there's a 4 outside, and a 5 is going to come out. Leave a little bit of space just in case we have to work on the y's, and we see that we have a 2 left over. Now, we have a power of 5. So we're going to take 5 and divide by 3. So it can go one time with a remainder of 2. So what does that mean? Y to the 1st comes out and y squared is left. Power comes out, this power is left underneath. So finishing the problem, we end up with 20y cubed root of 2y squared. Again, make sure you're writing that index every single time that it's not a square root. Alright, so the last one on this section, we have 3x squared, 4th root of 243 x to the 9th y to the 5th z. So we'll start off with 243. Well, 243, what can be divided into 243? That's going to be kind of a little bit harder to think. So you just kind of go through your numbers and see if 243 can be divided by 3. And it is. We can do 3 and 81. 3 is prime. 81 is 9 times 9, and neither of those are prime. So I'll move those on to 3's and 3. And so we end up with 5 3's. But we only need 4 of them to come out. So we're going to circle 4 3's. So one of the 3's come out and 1 3 is left underneath. And we still have a 3x squared out front. So we have a 3x squared out front. We took out a 3. We'll leave some space because of all the variables. And what's left underneath is this 3, this one right here. So then we're going to take power divided by index, and we do 9 divided by 4. It can go twice with a remainder of 1. So that tells me x to the 2nd comes out and x is left underneath. Then we're going to take the 5, and we do 5 divided by 4. It can go one time with a remainder of 1. So 1y comes out and 1y is left underneath. Now z only has a power 1, so it doesn't have enough to come out, so z is going to stay underneath. And I always draw a line through my z's. So now we'll finish the problem just by multiplying that out. 3 times 3 is 9. X to the, when we're multiplying, we add power, so we get x to the 4th y. And we have the 4th root of 3xyz. So lots of things happening in that problem. Make sure you can do them well. So those were just simplifying. We didn't have any really multiplication or division too much, but now we're going to get into multiplying and dividing with radicals. Again, to be able to do so, you have to have the same index. We have square roots, we have square roots, and we have square roots, so we're allowed to multiply. How do we multiply? We multiply the numbers that are outside, and we multiply the numbers that are underneath. So 2 times 5 is 10, square root of 6 times 21. Now again, just multiply those numbers outside and the numbers inside. So we get the square root of 126. Now can anything come out? Well, we know that 126 was 6 times 21. 6 is 2 times 3. Those are prime. And 21 is 3 times 7. If you don't know your multiplication well, this is going to be a very challenging section. If you know your multiplication well, you should be able to get down to your prime factorizations pretty nicely. So we're going to circle a pair, and a pair of 3's is going to come out. So as 3 comes out, what's already out there is a 10. So we have a 10, and then we have a 3 coming out. And then we have a 2 times 7, which is the square root of 14 left underneath. So our final answer is 30 square root of 14. So on number 2, we have a 6 on the outside and a 2 on the outside, so that's going to give us a 12 when we multiply. and we have 15 times 10, which is 150. And when we're multiplying, we add power, so we get c to the 7th, because 3 plus 4 is 7. I know it seems like we're doing an extra step by multiplying it and then going back to doing your factoring, but I definitely want to challenge you to do it this way, because if you start trying to simplify here, and then nothing simplifies, and then you have to multiply, and then you have to simplify again, it really does make more sense to multiply and then simplify it just one time. So 150 would be 15 times 10, and 15 is 3 times 5, and those are prime, and 10 is 2 times 5, and those are prime. So as we can see, we have a pair of 5s. So we have a 12 on the outside, a 5 is going to come out, we'll leave a little bit of space for the variable, and then what's underneath is that 3 and that 2. So 3 times 2 is 6. Now what do we do with the variable? We take power and we divide by index. So we take our power 7 and we divide by our index 2. It can go. What does that mean? That means c to the 3rd comes out and c to the 1st stays underneath. So 12 times 5 is 60, c to the 3rd, square root of 6c. So I'm going to let you do number 3. I will give you the answer, and hopefully you can get to it. It should be 24c to the 4th, square root of 15. So try number 3 and make sure you can get to 24c to the 4th, square root of 15. Alright, so now find the quotient. Quotient means to divide. So when we divide, as long as we have again the same index, we can put them underneath the same radical. So those are the same index. We have index of 2 and we have index of a 2. So everything should be okay. First things first, when you take 10 and divide by 2, we get a 5. Those are on the outside, so let's go ahead and divide it. And then we have 280 divided by 10, now under the radical. So then we end up with 5. 280 divided by 10 is 28. And now we do the factor tree. 28 is 4 times 7, 7 is prime, 4 is 2 times 2. So we have a pair of 2's and we have a 5 on the outside, so 5 times 2 and then square root of 7. Again, the reason why only one 2 is coming out because this is really 4 and the square root of 4 is 2. So we end up with 10 square root of 7. So I'm going to let you try number 2. I will give you the answer. The answer is 8n squared. Just a reminder, when you're dividing, you subtract exponents. So when you put these together, just make sure you subtract exponents. Alright, so number 3, we actually have multiplication and we have division. So the best thing to do is just multiply straight across. 5 times 10 is 50. And y to the, we have 3 plus 6, we get 9. All over 3 times 27 is 81. Now when they're together, we look to see if we can reduce the 50 and the 81, and we cannot. We can't do anything because there's no y's on bottom, so we're going to re-separate them into the square root of 50y to the 9th, all over the square root of 81. We know there's a nice square root of 81. The nice square of 81 is 9. Well, let's look at 50. 50 is 5 times 10. 5 is prime. 10 is 5 times 2. So we see we have a pair of 5, so 5 is going to come out, leave some space for the variable, and a 2 is going to be left underneath. Then we take our power divided by our index. 9 divided by 2 can go 4 times with a remainder of 1. So what does that mean? That means y to the 4th power goes out, y to the 1st power stays underneath. If we could reduce the 5 and the 9, we would, but we cannot reduce those since there's nothing in common, so we are done at that point. You don't have to have the 1, but you can leave it there if you'd like, but it's understood to be there.